All right, so in this example, we're again going to be looking at showing one of these really big, nasty logical equivalences, and we're going to try to attack this thing using some of these known facts. What makes this problem a little bit more annoying is that left-hand side of this object is really gross looking. If you look at it, you can see that there's this conditional statement that's nested inside of another conditional statement. You have this P implies Q, and then that becomes the hypothesis that leads towards R. So if you step back and think a little bit, why would you ever care about having some kind of horrible nested if-then statement? Well, for those of you that have seen some programming, or for those of you that are going to go and see some programming in the future, this type of structure occurs all over the place. You have this kind of initial if-then statement, and then if something satisfies within that thing, you're going to lead towards another outcome. So you can think about having these if-then statements nested very large. You've got kind of this giant chain. So it might look bad in this case, but they can go much worse. You can nest this multiple times. What this type of logical equivalence allows us to do is it allows us to decompose this thing. So rather than having this kind of giant nested structure, what I can do is I can break this into two separate if-then statements, which is sometimes a nice thing to do. Sometimes avoiding this nesting is going to be kind of advantageous for speeding up some of our algorithms and things like that. So in this case, it's going to allow me to rip this big nested if-then statement into two separate little if-then statements separated by an and. In this case, I'm going to have a not P implies R as well as a Q implies R. So let's go ahead and see if we can dive into actually showing this thing. In this case, we're going to try to use some known logical equivalencies to actually attack this thing. Like I mentioned earlier, the left-hand side looks way worse, so that's going to be the side that I'm going to start with. The idea for this is going to be to unpack that left-hand side, explode it out into a whole bunch of little pieces, and then try to recollect things as you go. Okay, so let's see if we can start this off. So I'm going to have my solution. I'm going to have P implies Q, and that's going to imply R. What I want to do is I want to look at this P implies Q. I'm going to convert this to an OR. And the thing that we're going to use many, many times in this problem is going to be this second conditional statement. It's this ability to take a conditional and convert it to an OR. The idea is that P implies Q is logically equivalent to not P or Q. We've actually seen the other version of this as well, so you're going to see this kind of negation coming into play, this other blue version. That'll happen a few times as well in this problem. So kind of keep that in the back of your head. This idea to go back and forth between ORs and conditionals becomes very powerful in these types of problems. So that's what I'm going to apply first. I'm going to do this on the inside part of this thing, and then I'm actually going to attack it on the outside as well. So first off, what's going to happen is I'm going to have the negation of P or Q. I'm applying that conditional statement 2 directly to that inside part. I'm not touching this implies R portion at all. Not yet, at least. So that was conditional statement 2, which says A implies B is logically equivalent to not A or B. What I'm going to do now is apply that exact same property, except for this part is going to become my A in quotes in this case. So what's going to happen is I'm going to have the negation of my hypothesis or my conclusion. So the exact same property, this conditional statement 2, is going to be applied one more time. Well, now if you look at this thing, hopefully the De Morgan's law is starting to kind of scream at you, and if it hasn't yet, you got to do a whole bunch of them to kind of see this giant OR that's inside of this huge negation. What you want to do to this thing is attack it with this negation. It's awkward to have this giant negation on the way outside. It's nice to bring that negation operator on the inside. And that's exactly what De Morgan's allows me to do. I can bring this negation inside of something that's separated by an OR. What's going to happen is that both pieces are going to pick up a negation operator, and the thing in the middle is going to switch. Right now it's listed as an OR, so it's going to become an AND. Giving the negations in, I'm going to pick up a double negation actually on that P, which we know how to handle. The middle part's going to flip into an AND. I'm going to have a negation of Q, and then that OR R is still going to be hanging out on the outside. So this was using De Morgan's. Okay, next I'm going to attack that double negation on the P to just write this as P and not Q or R. So that's going to use double negation. All right, so now we got to think a little bit about what we want to do next. At the end of the day, the right-hand side of this expression is in a sense two separate pieces. They're separated by this and. That's kind of the big goal of this thing, was to take this horrible nested if-then structure and rip it into two little pieces. Well, now I'm still kind of at the stage where I have one piece. What I want to do is somehow rip this into two pieces. Well, the ability that we can kind of take one object and split it into two is typically going to come down to a distributive law. If you think back to your days of algebra and things like that, this type of distributive law occurs all the time. If you try to multiply x across to everything, what's going to happen is you have lots of little pieces afterwards. It's kind of the opposite of factoring. I'm going to explode pieces into little bits. What I'm going to do in this case is I'm going to apply this distributive law that takes this OR and it distributes it across any of these ANDs. In this case, I'm going to think about bringing this P into this object, and I'm left with P or Q and P or R. So that's exactly what I'm going to do here. I have this distribution of this OR with the R. Officially, it's written on the right-hand side of this expression, and the theorem has it on the left-hand side, but that's totally fine because we know that these ORs are actually going to be commutative. That is, A or B is the same thing as B or A. It doesn't matter which side it's on. You can have it on the left side or you can have it on the right side. In this case, I'm going to leave it on the right-hand side because up here, all of those R's are written on the right-hand side as well. So it's going to become a little bit easier to kind of package everything back up. So in this case, I'm going to distribute across. I'm going to end up having a P or R. There's going to still be this AND, not Q or R. So that thing is going to go into here, and it's going to go into there. So here's where I'm using my distributive law. Or this kind of, I guess, 1, 2, 3, 4, fifth property in this last theorem. Okay, so now I'm getting a little bit closer. I've now broken this thing up into two little pieces. I have this P or R, and I also have this not Q or R floating around. Now I just have to think back of, does this actually package back into what I want it to be? What I'm going to be using here is actually just this conditional statement 2 a few more times. We actually see one of them up here. It's this idea that not A or B, right here, not Q or R, is going to turn into A implies B. In this case, it's going to turn into a Q implies R. The same exact thing is going to occur over here, but the thing that's slightly different is that this one does not actually have the negation in front of the P. But we know how to handle that. That's actually the very first one that we looked at, is that we have this ability to go from P or Q. This converts into a not P or Q. It's the exact same rule that we see up here, except for we've replaced our P's with not P's. And everything works out nicely as well. So this part right here is going to convert into a conditional as well, except for they're still going to have a kind of negation operator floating around. So in this case, there's a negation here already, so when I convert it there, it no longer has a negation operator. Here it did not have a negation operator, so when I convert it back to a conditional, it's going to pick up that negation. And what's going to happen at the end of the day, it's still going to have an AND. I use my conditional statement 2, I officially use it twice in this case, to end up at this split version of these two separate conditional objects. And I think that's exactly what I want. Double check everything. I have a not P implies R, not P implies R, check. And then I have a Q implies R, which is exactly what I wanted to do as well. What's nice about these proofs is that when you're done with it, you can actually see how to go the reverse direction. If you would have started with the right-hand side, you can see that you could have packaged all of these things up, applied this distribution, done these kind of things in reverse, and still ended up back at here. I think it's a little bit more complicated. You can kind of try to sketch out that proof by looking at this in reverse, and you're going to see that there is a few more subtleties of going that direction. I think it's a little bit easier to just explode out all of these conditionals and then repackage things at the very end.